Hello, it's Keith here, and this is lesson 29 of the simple series of my Z80 assembly programming tutorials. We're looking at the Sam Coupe example again. Now, we saw it before, and we've got our bitmap, and we're moving it around the screen, and we're cropping, and we're not going to discuss the cropping this time. Episode 28 did that. What we're going to discuss is some of the tricks that are being used to make it faster and nicer. We're using Stack Misuse, and we're using this in two ways. One to speed up writing, and one to speed up reading, and we're also using a double buffer. This is where we have two banks of memory. We write to one while we show the other, and then we swap them over, so we get no screen flicker. We can take as long as we need to draw the graphics, and as I say, the Stack Misuse is speeding things up. Now, what is Stack Misuse? Well, this is where we use the stack pointer, and instead of using it as a temporary store of variables, we actually use it for fast reading or fast writing of data. The stack pointer, if we point it to a memory address and then we do loads of pushes, will fill a memory range. Equally, if we set it to the start of a range and we do loads of pops, we can read a memory range. So we can use the stack in those ways. Of course, while we're doing that, we can't use the stack really for storing temporary data. We also can't really use it for calls or interrupts. So that's a limitation. Not entirely true. If we're very, very clever, we can still just about do those things. I do have a tutorial in the multi-platform series on an interrupt handler, which covers how you can actually still use Stack Misuse and allow interrupts to keep running. But generally speaking, for simplistic, as a simple rule, you can't use interrupts. Okay, let's go over to our code and let's take a look at what we've got to see today. Okay, the first thing I think we want to discuss is the page buffering routine. Now, when we want to page in some memory to write to VRAM, let's just close our example there, we will need to use port 250. This will page in something into the first 32k of memory, and so we're going to have two buffers. One is going to be the first visible screen buffer and one is going to be the second. Now, these are two 32 kilobyte banks of memory, but actually only 24 kilobytes is used by the screen, so there'll be a little bit of spare, but we're not going to worry about that. Now, the first buffer we're going to use is this one here. Now, this is bank 12, but these are actually measured in 16 kilobyte banks, even though the bank itself is 32 kilobytes. So we're going to use 12 and 13 for one of our buffers and 14 and 15 for the other one. These go from 0 to 15 on the 128K system. So that is how we are selecting our banks that we're going to use. I'm just using these predetermined. So the minimum amount of memory the Sam Coupe has is 128K, so we know that will exist. So what we're going to do here is we're basically going to load in the current active buffer. We're going to assume this has now been drawn, and we're then going to show this to the screen, and we do that by outing that to port 252, which selects the visible screen buffer. We're then XORing bit 1, which is toggling this bit here, and so this is selecting between 12 and 13 and 14 and 15 as the current buffer. We're then storing that to active buffer, and it's active buffer which is the one we're actually drawing to at the moment. Now you can see the clear screen routine here, and this is at the very start loading in active buffer, and it's paging that in with port 250, which is loading it into the 0 to 7FFF range, and then we can write our data to it. Now, the clear screen routine is using Stack Misuse. Now, when we want to clear the screen, we are running this routine here. We're specifying the color we want to draw in with D and E here. So 4444 is that rather nasty green color. We're then specifying the end of the range we want to fill. Now, we want to fill 24K, and so this is memory address 6000 in hexadecimal. We're also specifying an amount of data we want to fill, and we're specifying 192, but this is actually to be multiplied by 128, and so this is effectively 24 kilobytes. So we're going to clear the entire 24 kilobyte screen. Now, why are we specifying the end of the range? Well, that's because we're using Stack Misuse. So what we're doing is we're loading the stack pointer with HL, which is the end of the range we want to fill. And then we're doing a big load of pushes to fill that range, because each push will push 2 bytes onto the stack, which is now our screen memory, or our screen buffer memory rather. But this is going to make the stack unusable, so we're disabling interrupts before we do this, and we're backing up the stack pointer. Now we want to transfer the stack pointer to IY, but we can't do that because there's no command to directly do that, but we can add the stack pointer to IY, and we just load IY with 0 before we do that. So that has now backed up the stack pointer with IY. Now what we're doing here is a big long sequence of pushes. Now each of these pushes will push 2 bytes, and we've got a big long sequence of them here, which is effectively pushing 64 times, that's 128 bytes. Why are we doing that so many times? Well, one reason is so we can use DJNZ, which can only go up to 255, of course, and so by doing this, we can use 192 in the B register. The other reason we're doing this rather than using BC is something known as unwrapping the loop. Now, a loop is very nice because it allows us to do things with just one, but we could just do this as a single push DE. But the problem with a loop is it's got a decrement command and a compare command built into that DJNZ. And those take a little bit of time. And if we're doing this thousands and thousands of times, that little bit of time starts to really add up. So rather than doing that loop thousands of times for our 24K memory range, we just do it 192 times and we do lots and lots of push commands instead. And so we're sacrificing the memory used by all these push commands and we're saving the speed that would be taken up by that DJNZ. If we did a decrement of B and C or something, it would take a lot longer. So, and this is often the sacrifice you make with 8-bit programming. You can either have speed and you lose memory, or you can have memory and you lose speed. You usually have to trade off in that way. And so often what you want to do is you want to get your game working and then start to see how much memory you've got spare and then start to see what kind of speed ups you can make, like this one here. So this is basically doing that. Now, at the end of the routine here, we're just paging in the ROM again. So we're turning the ROM back on here just so that our keyboard routine can still work, because our keyboard routine in this example we're using the firmware one, so that ROM needs to be re-enabled. So that's how we're filling the screen with the stack pointer. And as I say, all we need to do to select the correct buffer bank is load in from the active buffer, which is being modified here, and we just send it to port 250. So actually very easy, the page flipping in this example. So there we're using stack misuse to fill an area of memory, but we can also use it to read memory. Now, in the alternate version of our show sprite routine here, this is going to use the stack pointer as a fast way of reading in bytes. And to be honest, I don't think this is very efficient here. It's probably not worth it with XOR, but if we weren't using XOR and maybe we weren't using cropping, I think it probably would give a speed boost. But anyway, let's have a look at it. So again, we're paging in the screen buffer into the low memory area here with port 250. We've disabled interrupts for two reasons. Firstly, we don't want that ROM interrupt handling while we are messing with the low memory area, but also we're going to misuse the stack, and that means we can't have any calls happening. And that's why the get next line routine is executed with a jump rather than a call, and the end of the get next line routine jumps back to get next line return rather than returning, because we can't do any calls or returns because they use the stack and we've messed with the stack. Okay, so rather than use IY, because IY is doing something else, we're backing up the stack with self-modifying code. We're storing the stack pointer to this memory address -2, and you can see that's immediately after a stack pointer load, so that 0 will be modified with whatever the stack pointer was at this point. We then load the stack pointer with the source bitmap data, and what we're going to do is we're going to pop off the stack DE, and then we're going to use that as bitmap data to put to our screen. So we're loading in from E here, XORing with the screen and storing it to the screen, incrementing L, which is the screen destination, loading in from D, XORing with the screen, and we're storing back to the screen. Now, I don't think this is very efficient. If we were not using XOR, we could make this a lot nicer. We could just do the pop DE, and we could load in E here and load D here. If we just run this here, where you can see our XOR is gone, but our Chibico is still drawing to the screen just fine, and that is going to be a very efficient way of getting bitmap data to the screen, because we've got that IncL rather than HL as well. So I think in this case, stack misuse is probably better than LDI, but in the other case, it's not. It's certainly not. And one case where this is definitely very good is if you wanted to do things like transparency or clever tricks like that. LDI is very fast. LDIR isn't so great, but LDI is very fast. But if you want to do things like transparency, you know, where you are loading in data and then doing things, the pop DE is possibly quite useful to you. Now, after each line, we are going to have to modify if we are cropping, and we're doing that again here, but this time we're going to have to do things a little bit differently. So we're loading HL again with the amount which we need to remove after each line. It will be self-modified with a value of 1 or 2 or 4 bytes rather, because we're working in pairs of bytes. So adding that to the stack pointer to that, and then we're flipping the HL back into the stack pointer. This means the stack pointer is now correct for the next sequence, and of course when we start popping our bitmap data, we will be loading the correct data in next time. So there we go. So that's how we are doing things. Of course, the last thing to do is just restore the stack pointer. Using the stack pointer in this way is a little bit weird, and as I say, I certainly wouldn't recommend you start doing this. And if you're just getting started, just use a regular one. Leave stack misuse and things for later. You're going to want to get your game working at first, and then once you get your game working, you want to make it as fast as you can and make some optimizations. But don't make things harder than you need to in the early days. The other thing I would recommend is I wouldn't combine things like stack misuse and cropping in the same routine. Chibi has had a wide variety of different sprite routines that you could have used one to do all of them, but it had a slow one that could do cropping, that could do transparency. It had a fast one that couldn't do transparency. It had a fast one that could do transparency, and it also had fixed width ones so that there weren't any horizontal byte counts. And there were lots of these, and as I say, by using lots of different routines, I could optimize the speed, but I was sacrificing memory when, as I say, in theory, I could have just used that one slow routine for all the jobs, but you're sacrificing speed and trading it off for memory, as I say. And anyway, as I always say, go to my website, download the source code, the build scripts and all of that, and have some fun with it. And if you can use any of this in any of your own projects in any way, go ahead, you're welcome to do so. I really wish you the best with it. Anyway, I hope you've enjoyed what you've seen today. Thanks for watching, and goodbye.